All right, this week we're going to review adding and subtracting and later on multiplying polynomials. So to add polynomials, I always like to think of each expression as being contained in parentheses. For addition problems, this isn't really all that important, but it becomes very important in subtraction problems. So here we have a polynomial, and it's being added to another polynomial. And if you think of them as being in parentheses, then the first step would be to eliminate the parentheses by applying the distributive property. And if there are no outside terms, then you can think of them as being invisible ones. So let's take a look at this addition and subtraction problem. All right, if we were to distribute these invisible ones, all right, in the addition problem, nothing really would happen. We'd still be left with 2x squared minus 5x plus 1, and then negative 3x and positive 5. But in the subtraction problem, all right, the first polynomial would stay the same, 3x squared plus 7x minus 5. And then the negative one would distribute, and all of the signs in the second expression would flip. So that would be negative 2x and positive 9. Now, once we've gotten rid of parentheses, all of our terms are free to associate with each other. And so we can combine the ones that are alike, giving us 2x squared minus 8x plus 6 and 3x squared minus 5x plus 4. And that's really all there is to adding and subtracting polynomials. So why don't you try to, on your own, just to remind yourself and to ensure that you remember all this stuff. So pause the video and try these problems now. All right, let's see how you did. So again, first step would be to distribute those invisible ones. The addition, excuse me, in the addition problem, nothing really changes. We keep all of our terms. In the subtraction problem, our first polynomial stays the same, and our second one has all of the terms, the signs of the terms flipped. So the negative 2x becomes positive 2x, and our negative 11 becomes positive 11. And once we combine them, we get 4x squared plus 2x minus 5, and 5x squared minus 2x plus 4. Now, let's put this in a little bit of a context. So let's say we had this nice little triangle, and we wanted to write an equation for the perimeter of the triangle. How might we do that? Well, the perimeter is just the sum of the three sides. So we could write something like this. The perimeter equals 2x minus 3, that's one side, plus 3x squared plus x minus 1, that's another side, and then plus x plus 2, that's the third side. Now again, this is all addition. Excuse me. That's all addition, so parentheses don't really matter, but I highly suggest you always use parentheses for several reasons. One, it organizes your information, and also it's very clear from this equation or from this expression that how it relates to the problem. Each parenthesis represents a side of the triangle. So now we'll distribute our invisible ones. Now we've freed all the terms from the confines of the parentheses. They're free to associate with each other. Some of them are going to like each other because they're alike, so they're going to combine, and we get 3x squared plus 4x minus 2. Now, is this the right answer? Seems like the right answer. I don't think I made a mistake. I feel very confident, but I don't have any evidence. So one way you can check yourself, all right, is to choose a value for the unknown variable, and if you plug it into the original expression, 2x minus 3 plus 3x squared plus x minus 1 plus x plus 2, you plug in that 2 and evaluate it, all right, you get a certain perimeter based on that input x. So when x equals 2, then the perimeter of this triangle equals 18. Now, if we take this simplified version, once we simplify this whole expression, all right, if this really is an equivalent expression, well, then when we plug in that 2, we should get the same value, and sure enough, we do. And so this gives me peace of mind that what I did created equivalent expressions. So I know I have the right answer. And you can use this technique anytime you want to determine if two expressions are equivalent, at least until you get to Algebra 2. And then there's some special cases you need to worry about. Basically, when x is in the denominator, all right, things can get a little Little hairy. All right, moving on. Multiplying polynomials. All right, we all know how to multiply. So let's revisit multiplication. So you may remember this from in class. We got students A, B, and C, and they were asked to find the product of 27 and 54. And I'd like you to look at the three approaches and compare and contrast what they did. Now, I'll just talk through this because we've already had this discussion in class. Student A seems to be using what's commonly known as the standard algorithm. So 4 times 7 is 28, carry the 2. 4 times 2 is 8, plus 2 equals 10. So you put that little 10 there. We had the 8 there. That gives us 108. So 27 times 4 is going to equal 108. Now, we're dealing with the tens place, so we add that 0. All right, and then we multiply by 5 or 50. 5 times 7 is 35, so we put the 5 there, add the 2, add the 3, or I should say carry the 3. 5 times 2 is 10, plus 3 is 13, so we put our little 13 there, and so we know that 27 times 50 is 1,350. So we've done two operations here, 27 times 4 and 27 times 50. We get these two values, you take their sum, and you get 1,458. That's the standard algorithm. All right, student B took a different approach. All right, student B multiplied by place value. Essentially, rather than doing two different operations, student B did 4. All right, 4 times 7 is 28. 4 times 20 is 80. 50 times 7 is 350, and 50 times 20 is 1,000. And summing those values up, we get 1,458. Now, student C used what's called the area model. Now, area is a wonderful, wonderful model for illustrating multiplication. So multiplication is just repeated addition, and anytime you have multiple instances of the same value, graphically this always makes a rectangle. All right, and it's analogous to the area of that rectangle. So what is the area of the rectangle with a length of 54 and a width of 27? Well, we can model this by expressing the length as 50 and 4, because that's what 54 means, and the width as 20 and 7, because that's what 27 is. All right? And that creates 4 very nice little quadrants here, all right, where we can find the area of each little quadrant in a very, very simple way. You might see a relation between what student C is doing and what student B is doing. So here we go. 50 times 20 is 1,000. 50 times 7 is 350. 4 times 20 is 80. And 4 times 7 is 28. And when we sum up those values, we get the whole area of the rectangle, which is 1,458. So let's discuss which method would probably be the approach we should take if we wanted to multiply two values like 27 and 54. So the standard algorithm is definitely the quickest. We did the least amount of work, but it is the approach that is most far removed from what actual multiplication is. It's just a bunch of instructions that gets you the right answer. All right, student B used place value to multiply, but notice student B had to know to kind of multiply the 4 by 7 and the 4 by 20 and the 50 by 7 and the 50 by 20. Why are we doing that? Honestly, why are we multiplying all of these values by all of those values? You might intuitively understand, but it's hard to put into words without actually using this area model that student C used. And so this is the one that's closest to what multiplication actually looks like in the real world if you wanted to model it in the real world. It's the least abstract version, all right, or the most concrete. And so the one that you can conceptually connect with probably the most. All right, so what we're going to do is we're going to use this approach today to try and build some ideas about how to multiply polynomials. So let's use the area model of multiplication to come up with a rule to multiply polynomials. So what is the product of x plus 5 and x plus 2? So here we go, x plus 5 times x plus 2. Let's create our area model and see if we can find the product. Pause the video and try it on your own. All right, let's see how you did. So x plus 5 is just x and 5. X plus 2 is just x and 2. And finding the area of each section of the rectangle, we get x times x is x squared. X times 5 is 5x. 2 times x is 2x. And 2 times 5 is 10. So adding all this together, we get x squared plus 7x plus 10. Let's try another one, this time on your own. Pause the video now. All right, let's see how you did. So we're doing 2x plus 9 times x minus 3, or x and negative 3. All right, so this is what you should have done. 2x and 9, x and negative 3. Found the area of each little subdivision of the rectangle and added them all up. And their sum is 2x squared plus 3x minus 27. Now let's use some variables to model any situation where we're multiplying one binomial by another binomial. So what is a plus b times c plus d? Pause the video and try to come up with the model now. All right, so a plus b times c plus d. It's going to look somewhat like this. A and b times c and d. And that gives you AC, BC, AD, and BD. And adding those all up gives you this. Now there's no like terms here, but if you notice, there are common factors. So here we have a little c and a c. Over here we have a d and a d. And when you have common factors, we know that we can factor those out. So, oh, I'm sorry, I'm doing this a different way. So I rearranged these so it's so the common factors are a and the common factors are b. So we're going to factor out that a and we're going to factor out that b. And what we have is a times the sum of c and d plus b times the sum of c and d. And what we've proven is this first statement, a plus b times c plus d, is equal to a times c plus d plus b times c plus d. And so really all we're doing here is we're distributing a to c and d, and we're distributing b to c and d. And if we understand that concept, there's no reason to rewrite our expressions. All we need to do is take our original expression and distribute a to c and d, and distribute b to c and d. So let's try using this on an actual set of binomials. So here's our two binomials that we multiplied using the area model. Now we know why we're distributing. So we're going to take x and we're going to distribute it to x and then to 2. That gives us x squared plus 2x. We're going to distribute the 5 to x and 2, and that gives us 5x and 10, and that gets us x squared plus 7x plus 10. We did the same here with 2x and 9. We distributed both to x and negative 3. That gave us 2x squared minus 6x plus 9x minus 27. Combining the two middle like terms, we get 2x squared plus 3x minus 27. Now let's try a few on your own so you know what you're doing. All right, pause the video now. All right, let's see how you did. So for the first one, we distribute the x and the 4 to both x and 9, and we get x squared plus 13x plus 36 after we've simplified. All right, next one, we distribute the 3x and the 5 to x and negative 2, and that gives us 3x squared minus x minus 10. And finally, 5x minus 3 times 2x minus 4. After distributing, we get 10x squared minus 26 plus 12. So let's revisit our earlier problem and apply our understanding to multiplication. What is the product of 27 and 54? Well, now that we know how to multiply polynomials and we understand how the area model works, let's see if we can represent this problem in a slightly different way. 20 and 7 is our 27. 50 and 4 is our 54. Now, how would we go about multiplying 27 times 54? If you notice, we're probably going to use this property that we just derived. We're going to distribute the 20 and the 7 to the 50 and the 4, and now we completely understand why we're doing that. And that gets us our 1,458. All right, so which method best represents what occurs when values are multiplied? Well, multiplying using the area model explains why we're distributing the 20 and the 7 to the 50 and the 4. It literally gives us a foundation to understand why the 4 gets distributed to the 7 and the 20, and the 50 gets distributed to the 7 and the 20, and why it happens here as well. So if you've ever wondered why are we distributing all these values, we now have a solid understanding of how multiplication works and how to apply that understanding to the multiplication of polynomials.